30th lecture, and we are going to discuss advantages of negative feedback amplifiers. Advantages of negative feedback amplifiers. Now, as far as feedback is concerned, whether it is positive or negative shall be determined by the sign of A beta. And you recall that our general block diagram was that we have an XS and an XF, both are taken with a positive sign. This is XI, and then you have the basic amplifier A, the output is X0 through a, what do you call this network? Sampling network, which we show simply as a line. We take a beta network through which is transmitted the signal XF, and the basic assumptions were that A was a forward looking device, it transmits in the forward direction, and beta transmits in the reverse direction only. Under these assumptions we derived the relationship that AF, the feedback gain, which is X0 by X of S, is given by the gain without feedback A divided by 1 minus A beta. And the the nature of feedback, whether it is positive or negative, is determined by the sign of A beta. Now, A beta can be complex, A beta can also be complex, okay, and that is when complications arise. If A beta is complex, it is frequency dependent, complications arise that at some frequency the feedback may be negative, at other frequencies feedback may be positive. Okay. So, if the feedback is to be negative, then we can do one of the two things. We can say A beta is equal to minus A1 beta 1, or we can simply change the sign here. Instead of positive, we can make it negative and say the gain would be A divided by 1 plus A beta. In the context of our discussions, it should be clear as to what we have done, but we are basically discussing negative feedback, because that is what is used in amplifiers. Positive feedback is hardly ever used except in the case of oscillators. Okay. So, one of the good effects of negative feedback is desensitization. Yeah. What was the Barkhausen? Oh, Barkhausen criterion was that if A beta is equal to 1 0 degree at some frequency at omega equal to omega 0, then AF tends to infinity and the circuit oscillates at the frequency omega 0. This is the Barkhausen criterion. The criterion is simply A beta equal to 1 0 degree. This is the condition, this is the criterion for oscillations at the frequency at which this occurs. Barkhausen, yes.
So, even if this is real A beta?
Even if A beta is real, yes.
Then it can be 1. What happens in such a way?
What happens then? Nuisance. Since it is satisfied at all frequencies, if it is real, you get noise at the output, that is all. Nothing else. All frequencies are present, which means all frequencies mixed together will be simply noise. If you accommodate the whole of IIT in this room, whole of IIT, obviously it would not make sense. But if you accumulate only second year electrical engineering students here and SCDR here, it is a EE 204 class, it is meaningful. Is that clear? Okay. If A beta is real, then all you get at the output is noise. And if it is an audio amplifier, for example, if it is an audio amplifier, you can speak as loud as possible on the microphone, nothing will be heard. All that will be heard is noise. Okay. So, one of the advantages of negative feedback, as I had said, is desensitization of the gain. Desensitization of gain with respect to device parameters and environment. we have already seen environmental changes. We have already seen manifestations of this in the case of the common emitter amplifier with an unbypassed resistor, but formally the sensitivity of any quantity, G with respect to any of its parameters x, G is a function of x, is defined as, this is the symbol that is used, capital S for G is the gain. G is the gain. Sensitivity of gain, I am using a general symbol. I don't want to use A or AF because I am going to use them later. The general definition is G can be any function, any performance parameter. It could be impedance, it could be admittance, it could be a gain, voltage gain, current gain, whatever it is. A performance parameter capital G is a function of the parameter x in the circuit. Then the sensitivity of G with respect to x is defined as x, well, let me give the definition first, delta G by G divided by delta x by x. In other words, if the parameter changes by a certain fraction, how much change does it affect on the performance? That's the definition, that's the qualitative definition. If delta x by x changes by 1% and delta G by G changes by 0.5%, then half is the sensitivity. Okay? So it is a an indication of how much x has an effect on the performance. Now as you can see, this can be written as x by G, delta G by delta x, and this delta G is a finite change, delta x is a finite change. Usually we find it convenient to make delta x to be infinitesimally small, delta x tends to 0, then obviously SGX would be x by G, differential coefficient of G with respect to x, and this is the measure that is very widely used. In practice we should use, for example, if you want to find the change of gain with respect to beta by device replacement, you know beta from one device to another can change by as much as 100%. So if you take two transistors, in one of them beta is 100 and in the other it is 200, obviously delta beta cannot be considered infinitesimal. Okay? So this definition will fail when delta x is not infinitesimal, but nevertheless we use this as a measure, as a convenient measure.
Shouldn't this be a partial derivative?
Okay, capital G is usually a function of not just one parameter but many parameters. So if I say capital G is a function of x1, x2 and so on, then the modification that you have to do is, if this is xi, then you have to put xi over G, and instead of small d you have to replace it by the curly d or delta, the partial derivative. This is very simple to follow, that if capital G is a multi-variable function, it is a function of many variables, then obviously total differentiation with respect to a parameter does not make sense, it has to be partial differentiation. Okay? And then the total change in G, delta G, has to be computed. Well, you cannot compute delta G, you can compute dG, total differential, that would be SGXI multiplied by dx summation of this. Into G by X? That's it. You have to multiply by delta xi, dxi. Agreed? Okay. So this is how it is done. Now in the context of our discussion of negative feedback amplifiers, we are going to consider one parameter at a time, and we shall not be concerned with the total change. This of course we have done when we are doing the bias calculations, bias stability, isn't it? We considered 3 parameters, VBI, ICBO and beta, and we found out the total change. Okay. Now in our case, AF is equal to A by 1 minus A beta, alright, and we want to find out the sensitivity of AF, the feedback gain, with respect to A. It is A which changes due to device change, device parameter change or environmental change, and you can easily show by differentiation and by applying the definition that this quantity is 1 by 1 minus A beta, and obviously this will go to 0 if A beta is very large compared to unity. Okay, this will go to 0, and under this condition obviously AF, if A beta is very large compared to unity, obviously AF tends to minus 1 over beta, that is the feedback gain is controlled by the beta network only, it is not affected by the gain of the internal or the basic amplifier. And one manifestation of this, many manifestations of this you have already seen. One of them, for example, is in this operational amplifier. If you have 2 resistances RF and RI, and your input is here, the output is here, this is grounded, the gain is A, and you know if A is large, there is a negative feedback through here, negative feedback through RF, and if A is large, you know that V0 by Vi is approximately equal to minus RF by Ri. That is, the gain is controlled only by the external resistors and by the feedback network. RF and Ri is the feedback network. Okay, this is one of the manifestations. The other was when you had the common emitter amplifier with an unbypassed resistor Re, then you had the gain was approximately equal to minus Rc by Re. This is also a manifestation of negative feedback. Desensitization of the gain of the feedback amplifier due to negative feedback. So this is one of the major advantages. The second advantage that we are going to consider is about reducing nonlinear distortion, NLD. This you must follow very carefully because there are tricky points where one gets deceived. For simplicity, we consider an ideal, yes.
So, how can we specifically say that it's only the negative feedback which reduces the sensitivity? It is also the positive feedback which can do the same.
Yeah, but before that happens, if A beta is very large, in positive feedback, the gain will take over. Okay, that's a good point. I was expecting this. In fact, when I was writing this, you must have noticed that I was slow in writing this because I was expecting a question. Nevertheless, better late than never. What he is saying is, this is not true only about positive feedback, only about negative feedback. It can also happen in negative feedback. I'm sorry, it can also happen in positive feedback, because what I have assumed here is magnitude A beta much greater than 1. Okay. Now, if A beta is positive, if A beta is positive, it cannot exceed 1. Isn't that right? If there is positive feedback, it cannot exceed 1, because as soon as A beta becomes 1, the circuit goes into oscillation or nuisance, as the case may be. Okay. Nonsense, as the case may be, and therefore it is not relevant to positive feedback. Alright, this desensitization is not relevant to positive feedback because the circuit no longer performs as an amplifier, it becomes an oscillator. Okay. Now, to be specific, we consider the basic amplifier as a voltage amplifier. That is, we consider Vs, Rs an ideal voltage amplifier, that is Ri is infinity. So, we have Vi which is equal to Vs and then we have AV Vi plus minus, that is it. This is V0 and the load is here RL, this is V0. We consider the basic amplifier as a voltage amplifier. Now, you know from your experience with voltage amplifiers that we have discussed so far, that this relationship, this ideal relationship between the output voltage and the input voltage, that they differ only by a constant, that their ratio is a constant, this can be valid only over a certain range of input voltages. Agreed? As soon as you go into the saturation region or in the cutoff region, nonlinear distortion starts, and therefore, if I plot the curve of V0 versus Vi, now Vi can go positive as well as negative. The curve would be a straight line passing through the origin. What is this origin? What does this origin correspond to? 0 input, that means the Q point. Okay. So, this origin actually corresponds to the Q point, and the curve would be a straight line like this only for a certain range of Vi. Let us say for this range, typically it could be 40 millivolts. Typically, let us assume a figure of 40 plus minus 40 millivolt. Okay. What will happen afterwards? As soon as we cross 40 millivolt limit, well, saturation or cutoff will set in depending on the polarity, and the curve will try to flatten off like this. Similarly, here also. Agreed? Now, if I apply negative feedback, suppose the gain is 100, let us take a specific case. Suppose the gain is 100, then the slope of this curve shall be 100, okay. dV0, dVi shall be 100 over the red region. As soon as it goes into black, the gain effectively decreases, drops down, okay. Suppose the gain is 100 in this region, and suppose the input Vi is equal to, let us say, 10 millivolt. What would be V0 then? 1000 millivolt, which is 1 volt, okay. Now, suppose we subject this amplifier, this basic amplifier, to negative feedback, all right, and let us say our beta is equal to 0.09, let us say, take some figure 0.09. Typically, this is the figure. I mean, it's a very small fraction of the output is fed back to the input. Then, with negative feedback, what is Vs corresponding to Vi equal to 10 millivolt? It would be Vi plus 0.09 volt, which is 90 millivolts. So, Vs required would be 100 millivolt for Vi equal to 10 millivolt. Is this point clear? With negative feedback, Vi is equal to Vs minus beta V0 with negative feedback. That is what I have done. To make a Vi of 10 millivolt, we have to apply a Vs equal to 100 millivolt. Agreed? If I want to make Vi, if I want to go to Vi limit, that is 40 millivolt, then how much Vs do I need? Okay, Vs would be 40 millivolt, 400 millivolt obviously. Did you have to make this calculation? No, you could have said this just by looking at the figure. So, now notice what I am saying. So, instead of plus minus 40 millivolt, instead of limiting the input voltage to 40 millivolt, we have to limit now Vs to 400 millivolt. Okay. Does this reduce distortion? Is it a reflection of distortion reduction? No, it is not. It is only a reflection of the property that the dynamic range of the amplifier is increased. Isn't that right? Instead of limiting your input voltage to plus minus 40 millivolt, you are now able to increase it to 400 millivolt. At what cost?
The gain is reduced.
The gain is reduced to how much?
10 times.
The gain is reduced by a factor of 10. Agreed? So there is no reduction of nonlinear distortion. It is only that the dynamic range is increased. All right? Oh, instead of limiting our input voltage to 40 millivolt, we are, because of negative feedback, we are able to increase the input voltage to 400 millivolt without nonlinear distortion setting in. Okay? So what we have done is, yes.
So you could have as well done this by a potential divider taking.
Of course. We could have done that, yes. So virtually we have gained nothing.
So are we limiting the input voltage or the source voltage?
Source voltage, yes. Okay.
The curve is in Vi and V0.
Curve is in Vi and V0. We can plot a curve Vi V0 versus Vs also. We can plot a curve. And that curve will be, what would be the nature of that curve? It would be linear with a less slope, and it would go right up to 400 millivolt on this side and 400 millivolt on the other side. Okay? The slope of this curve would be simply 10, because the gain was 100 and 1 plus A beta is equal to 10. Okay? It would be 1 plus A beta now because negative feedback. Alright, so we have gained nothing by this negative feedback. We have only reduced the gain and we have been able to increase the source voltage, the dynamic range of the amplifier. However, make an approximation to this characteristic through piecewise linear curves. That is, let's say you have this as the linear region, and suppose the gain here is 1000. As soon as you exceed the dynamic range, the curve tends to saturate. If you approximate that by a piecewise linear curve, let's say the curve goes like this. Okay? Obviously, if the dynamic range, if the input range goes right up to here and here, there will be lot of nonlinear distortion because of this kink in the gain curve. Let's say the gain here is 100. Okay? Now let's see what happens with negative feedback. Suppose the beta factor is, let's reduce it further. Suppose beta is 0.01. Then when the gain is 1000, what is the gain of the, what is the feedback gain? It is 1000 divided by 1 plus 1000 multiplied by 0.01, so it is 10. That is 90.9 approximately. Okay. So in this range the curve gets reduced, the curve gets flatter, the slope decreases to 90.9. Okay. So maybe it becomes something like this. Fine. What happens to the gain in this region? It becomes 100 divided by 11, which is
9.9. So divided by 10.
So 9.
Divided by 2. Sir. Divided by 2.
100 divided by 2. I beg your pardon. 100 divided by 2, because 1 plus 100 multiplied by 0., which is 50. And therefore the gain flattens off like this, maybe like this. Now a change of slope from 1000 to 100 and a change of slope from 90 to 50 by a factor of 2, previously it was a factor of 10. Therefore the nonlinear distortion in the feedback amplifier would be much less as compared to nonlinear distortion in the non-feedback amplifier. Is the point clear? This picture is worth a million words. It explains how nonlinear distortion is reduced. In other words, the transitions or the discontinuities are smoothed out by nonlinear distortion. And if you apply sufficient feedback and the gain was sufficiently large, you can make this curve almost a straight line. Okay, these kinks are reduced and therefore there is a reduction in nonlinear distortion. This is a qualitative picture. Now let us look at it quantitatively. What is the price that you pay? The gain. Gain is reduced by a factor of, in this range, 10 or 11? 11. The gain is reduced by a factor of 11. Now one can argue that this feedback amplifier that you have, AF, you have reduced nonlinear distortion by introducing negative feedback, and the factor is 11. So why don't you add an amplifier, a pre-amplifier of gain 11, such that this gain reduction is compensated for. Now this is a very tricky suggestion. You must make sure that this pre-amplifier does not introduce nonlinear distortion. Now would it or would it not? That is the question. Since the gain is small, the nonlinear distortion introduced by this pre-amplifier will be much less as compared to the feedback amplifier. Small gain, and therefore the excursion of voltage at the output will not go to cutoff or saturation, and therefore it is easy to design a low gain amplifier, low gain pre-amplifier, to compensate for the reduction of gain in the feedback amplifier qualitatively. Now let us look at it quantitatively. It is very important to establish this and be convinced that nonlinear distortion can indeed be reduced by feedback. Let us consider the usual feedback block diagram, the basic amplifier A, and now because of negative feedback we use a negative sign here. Alright, we use a negative sign here. This comes from the beta network. This is V0, this is Vf, we are now considering voltages, this is Vi, and this is the beta network. Now the occurrence of nonlinear distortion, obviously this block diagram is valid when everything is linear, and we can derive that V0 by Vs is equal to A divided by 1 plus A beta, because negative feedback has been assumed here. Okay. Now the nonlinear distortion obviously occurs in the amplifier and can be taken care of by introducing the distortion term as a summation term here. Let us say that the distortion voltage or distortion component of the output is Vd. Then obviously distortion can be shown in this diagram by means of an additional voltage Vd. And if you now analyze including Vd, then obviously V0 would be equal to AVi plus Vd. Is the point clear? AVi is the undistorted output, add to it the distortion. Okay, so the output becomes distorted. If you now analyze this circuit, you can show very simple algebra that V0 is equal to A Vs divided by 1 plus A beta, that is the undistorted output, plus Vd divided by 1 plus A beta. Now have we been able to reduce nonlinear distortion? Obviously not, because we still have A Vs plus Vd divided by 1 plus A beta. both the signal and the nonlinear distortion have been reduced by the factor of 1 plus A beta. So the relative values have not changed, right? The nonlinear distortion in the output has been reduced by the same factor as the signal. So the relative values have not changed. But suppose now we add another amplifier here, a pre-amplifier whose value is 1 plus A beta, and let us say the actual input source voltage is Vs prime, then obviously V0 would be equal to A Vs prime, okay, plus Vd divided by 1 plus A beta. I beg your pardon, this should be okay. No, this is okay. Is it ABS? It is ABS. That's right. If I multiply this, I can put it here or I can put it at the other end. Shall I put it at the other end, post amplifier? Yes or no? No, because then the distortion will also be. So I have to use a pre-amplifier with a gain of 1 plus A beta, and 1 plus A beta at pre-amplifier stage shall handle much less excursion of voltage than the basic amplifier, and therefore the nonlinear distortion in 1 plus A beta can be reduced, and I can regain the original amplifier gain A with a distortion which is reduced by the factor of 1 by 1 plus A beta. Okay? No? There is no distortion here, and therefore this voltage Vs is equal to Vs prime multiplied by 1 plus A beta. Alright? That is all the change.
The output should be Vs prime.
Output should be Vs prime. Okay. So what we do here is we consider this as Vs. Is it okay now? We have applied, instead of Vs, we have applied 1 plus A beta times Vs. Okay? Is the difficulty taken care of? Alright. So we convince ourselves by qualitative analysis. In qualitative analysis we look at the kink, and the kink is straightened out. Okay, so nonlinear distortion is reduced. Quantitatively we see that the distortion can be reduced by the factor 1 plus A beta by negative feedback. Yes, it's important that you understand this.
So in the qualitative distortion,
Yeah.
it did not give us any knowledge about the relative distortion in the signal. It was only after we quantitatively derived the formula.
That's right. This is why I wanted you to understand qualitatively first. Qualitatively what is happening is, if the gain goes like this, then with negative feedback these are straightened out. So it becomes more of a straight line than with a kink, and therefore the nonlinear distortion is reduced. Now is it not also obvious that if this amplifier generates some noise at the output, then this noise will also be reduced by the same factor? Is the point clear? If instead of nonlinear distortion, the distortion was due to noise, short noise, Johnson noise, whatever the source of noise is, noise at this point at the output of the amplifier, then obviously this noise will also be reduced by the same factor 1 plus A beta. But now, Ankur, this is for your attention. Now there is a problem. There is a problem. You cannot make up for the gain by a pre-amplifier. Why not? Because the pre-amplifier will have noise. Noise is omnipresent. It does not depend on the signal level. The noise generated by an amplifier, a device, a resistance, a capacitance, or whatever the device is independent of the signal, and therefore there shall be the noise generated by the pre-amplifier shall also be amplified. Okay? And therefore compared to nonlinear distortion, the noise reduction is to a much less extent. In other words, what you have to do is you have to design specially a pre-amplifier with a gain of 11 or whatever the gain is, which is noiseless. You have to take special components which generate less noise, or have a special architecture for this circuit which is a noiseless architecture. So noise reduction is not as easy as nonlinear distortion reduction. Okay, I also said that negative feedback controls impedance levels. This we shall illustrate with the help of again a very ideal ideal amplifier. Suppose you have a series connection at the input. Suppose you have a series connection at the input. You have a voltage source Vs, and then you have the feedback voltage Vf. Okay, I am looking at the equivalent circuit of the input Vf, and you have an Ri. Okay, the input resistance without feedback is Ri. What I want to find out, this is Ri. Let us say this is Vi and this is I sub I.
Polarity of Vf should be opposite.
If it is negative feedback. Okay, let us do that. Good point. Let us make it negative feedback, minus plus. Then what is the resistance, input resistance that is seen by Vs? Obviously it is Vs divided by I sub I, and Vs is Vi. What is the KVL? Vs equal to Vi plus Vf divided by I sub I. Agreed? This is negative feedback, and this would be equal to Vi plus beta A Vi divided by I sub I. Agreed? The feedback voltage is beta times A multiplied by Vi. Beta times V0, V0 is A Vi. Okay. So this is equal to Ri multiplied by 1 plus A beta. So in series connection, the input impedance increases by the factor 1 plus A beta, and this is independent of what the output connection is. Whether the output connection is series or shunt, it does not matter. Agreed? The input impedance increases with negative feedback if the input connection is series. Can you see it qualitatively? Why it happens? Yes? So the same Vs we have less current. For the same Vs we have less current because there is an additional source here. Agree? Qualitatively this is obvious, but this is the quantitative relationship, that the input resistance Rif is equal to this. By the same token, can you now say that if the connection was shunt, negative feedback with input shunt connection, then what will happen to Rif? Shunt at input. Shunt means current is being taken away, or another additional impedance is coming in shunt, in parallel. So the input impedance should decrease, and it is very easy to prove that if it is shunt at input, then Rif is Ri divided by 1 plus A beta. Once again it is negative feedback. It is very easy to prove. I will skip this proof if you do not mind. What can you say about the output resistance? Again, you can do it quantitatively, but qualitatively you see that if the output resistance R0, if the connection is series, then the output resistance would increase or decrease. If it is series, it increases. Why is it so? Because if the connection is in series, let me draw the amplifier. You have the basic amplifier then you have the load, and then you have a series connection. This goes to the feedback network. So the output impedance that is seen by the load is not only the output impedance of the basic amplifier, but it is added to the impedance that it sees here, and therefore the output resistance effectively increases, and this increase is again by the same factor 1 plus A beta, and this increase is independent of whether the input connection is shunt or series. It does not matter. If the output connection, sampling connection, is a series connection, then the output impedance increases. In a similar manner, if it is a shunt connection, R0 shunt at output, then the output impedance ROF, pardon me, decreases by the same factor 1 plus A beta. I leave these proofs to you. Please do try to establish them. Okay.
So all these results only hold for negative feedback.
All these results hold for negative feedback. Yes.
So positive feedback just change the sign. Minus.
That's right. In positive, but make sure that A beta is less than 1. That A beta is never allowed to exceed unity. If it is allowed to exceed unity, then the whole amplifier falls to the ground. It can be junked. Okay. Now, I also told you that a negative feedback increases the bandwidth of an amplifier. It helps to improve the bandwidth of an amplifier, and that is very easy to establish. Suppose we consider the high frequency response of an amplifier. At high frequencies, an amplifier A of S is of the form A0, the midband gain, divided by, yes, 1 plus j omega by omega h. We replace j omega by s, so it becomes s by omega h. Agree? Midband gain is A0 and the 3 dB point is omega h. We replace j omega by s. We work in the Laplace domain. Okay. This is the expression for the high frequency gain of an amplifier. Now take AFS, which is A of S divided by 1 negative feedback. So plus beta, we assume that beta is resistive, that is beta is not a function of frequency, beta A of S. If you substitute this in this relation and make some simple algebra, the result is AFS becomes equal to A0 divided by 1 plus A0 beta. This is expected at midband. This must be the gain, divided by 1 plus S divided by omega h multiplied by 1 plus A0 beta, which means that the omega h with feedback increases by the factor 1 plus A0 beta. Okay. At what cost? The gain. The gain is reduced by the factor 1 plus A0 beta. So what you gain in bandwidth, you lose in gain. Is that clear? It's a trade-in. You want more bandwidth, you sacrifice gain. The product, obviously you see AF0 multiplied by omega HF, this product is a constant. It is equal to A0 omega h. Isn't that right? Okay. This is another example of the uncertainty relationship that you have, the famous uncertainty relationship of physics, that you cannot increase both simultaneously. Okay. On the other hand, if you look at the low frequency gain, at low frequency, what is the transfer function? A of S is A0, then 1 minus j omega L by omega. So I can write this as 1 plus omega L by S. Don't bring in a negative sign here, because that will make a pole in the right half plane, and the system will automatically be unstable. The expression was A0 divided by 1 minus j omega L by omega. Now it can be written as 1 plus j omega, and j omega is replaced by s. So the pole is at s equal to minus omega L. It must be in the left half line. Okay. So if I now substitute in this AFS as equal to A of s divided by 1 plus beta A of s, then you can very easily show that AF of s becomes equal to A0 divided by 1 plus A0 beta. As usual, the midband gain becomes this, and what we have is 1 plus omega L divided by s times 1 plus A0 beta, which means that omega L with feedback becomes equal to omega L divided by 1 plus A0 beta. So the low frequency 3 dB point decreases, which means that the total bandwidth increases. Okay. So if I have without feedback a gain curve like this, then with feedback it would be like this. The bandwidth increases by the same factor as the gain reduction. Okay. So what you gain in bandwidth, you lose in gain. Yeah.
So the pre-amplifier stage should have a gain of 1 plus A0 beta.
That's right. Pre-amplifier stage should have a gain of 1 plus A0 to be able to bring the gain back to the previous quantity. I want to draw a couple of examples of feedback amplifier, practical feedback amplifiers, and just to give you a test of what a practical feedback amplifier looks like. But in this drawing I will skip the biasing parts. You can draw that separately. I will only draw the signal part. Okay. A typical feedback amplifier may be like this: IS, RS. This could be a high impedance source. High impedance source we usually model as a current source. Can you give me an example of a high impedance source in practice? A capacitive transducer. In a measurement, if you use a capacitive transducer to transfer, let's say, mechanical strain to an electrical signal, capacitive transducer is a high impedance source, or even a microphone is a high impedance source. Okay. Now suppose we have a two-stage amplifier like this, Q1. This is what I mean by excluding the biasing circuits. I am only drawing the AC, the signal circuit. For the biasing I have to show VCC, I have to show how the base is biased and things like that. I skip all those. I only show the AC equivalent circuit. And then you have a Q2, another transistor in which there is a resistance R sub E which is unbypassed. Okay. And the Q2, this is RL2, and this current is I0. The output current is I0. Okay. RE is a small resistance. RE is a small resistance. Now if I want to apply feedback to this, what kind of amplifier is this? Current to current. It is this current which is of importance. Current to current. So it's a current amplifier. Okay. It's a current amplifier, two-stage current amplifier. I0 is the quantity of interest. Now if I want to apply feedback, a sample of the current is to be taken. In other words, I have to make a connection from here. I don't want to do that, because if I do that, then the feedback will depend on the load. Isn't that clear? So what I do is I take an approximately equal current. You know this current is approximately equal, the emitter current. It's I0 divided by alpha, where alpha is approximately 1. So I sample this current. Now I don't sample the current as a current. I use a small resistor here to drop a voltage which is proportional to the current, and this is what is applied here through a resistance, let's say RF.
So
Yes.
if I0 is dependent on RL, so is emitter current.
Pardon me?
If I0 is dependent on RL too.
Right. If I make a connection here, obviously the effective RL will be disturbed. I don't want to do that. So I use a small resistance here and make this connection here. Okay. Now what is the kind of input connection here? Series or shunt? Series. Okay. Let this current be IF. This current II, if RS is not there, is obviously IS minus IF. So it is negative feedback. How do you know it is negative feedback? Because I could have drawn IF in the other direction also. No. For that you have to do a little bit of analysis, and I will do it in half a minute. Suppose IS increases. Suppose IS increases. This will make II increase. Okay. And this will make the collector current of IC1 increase or decrease? Increase. If the collector current of IC1 increases, what about this voltage? The load voltage? No. It must decrease. Current increases, so the collector voltage decreases. If the collector voltage decreases, then what happens to I0? It decreases. If I0 decreases, then this voltage, if you call this VE decreases. And if this voltage VE decreases, then what happens to IF? Increases. In other words, a tendency of IF to increase is arrested, which means that it is negative feedback. This is called a qualitative loop analysis, and it requires much more than analytical ability. It requires intuition. It requires careful consideration and application of the strongest tool of an engineer, namely common sense. More on 11th.